Good afternoon, everybody. Take your seat. In the interest of time, we'll get started, and we'll welcome everybody else who's going to flow in. I'm Shlomo Zilberstein from UMass Amherst, and it's my great pleasure to introduce the next invited speaker, Danica Kragic. Danica is a professor at the School of Computer Science and Communications here in Stockholm at the Royal Institute of Technology. She received her master's in mechanical engineering from the Technical University of Rijeka in Croatia, and her PhD in computer science from KTH. She's the director of the Center for Autonomous Systems. Her research is in the areas of robotics, computer vision, and machine learning. She received the 2007 IEEE Robotics and Automation Society Early Academic Career Award. She's an IEEE Fellow, a member of the Royal Swedish Academy of Sciences, the Royal Swedish Academy of Engineering Sciences, and a founding member of the Young Academy of Sweden. And without further ado, please welcome Danica Kragic.
Yeah, perfect, thank you. So thank you for the introduction. Today I will be speaking about and presenting the work that I have done together with my group for the past 5-6 years. So I won't go back too much in time in order to, in this next coming 40 minutes, come to these days and what we are doing today. My work focuses very much on physical robots, equipping robots with the capability to interact with the world, to interact with the human, and also to interact with each other. The video on your left-hand side is a video from one of the preparations for the Amazon Picking Challenge. So we worked with PR2 robot, equipping it with the ability to detect objects, place them in a box, and so on. On the right-hand side is one of the tasks that we would like robots to do in the future. The ability to interact with a human, that in this case is preparing a dove. And the role of the robot here is to observe humans' interaction with the environment, in this case with the dove, and understand from the perceptual cues whether the human needs some form of physical help or through dialogue, and also to understand and help the human in a proper manner. So trying to understand whether the human, for example, needs more flour, by understanding that in this case sticky fingers mean that the dove is not yet done. So the tasks that we are looking at are, again, making robots autonomous and making robots collaborative, and collaboration also requires lots of understanding of the ways that humans interact, but also understanding of the physical world, so how things or objects are behaving when humans or robots are interacting with this. And we have been doing this for quite some time, and we have been doing this with different types of robots, and I think that this is one of the big challenges that many of us are facing today in the area of robotics. And this is the status of hardware. So our interest has always been to work with mobile manipulation, with robots that have 2 arms. And if I look back approximately 20 years when we started to do this, having dual-arm robots equipped with different types of sensory capabilities, from vision, old stereo systems now changed to 3D perception, and was never enough. So looking also into force torque feedback, tactile feedback, and also trying to understand how the embodiment of the robot enables robot to do different things. So understanding the limitations of its own embodiment. Like in example on the upper left, robot understanding that it cannot grasp a spatula from the table without doing something that we called for pre-manipulation. So preparing the object, bringing the object in a position or in pose from which it can be safely manipulated. Also, we think very much about how learning and interaction in robots can be properly implemented. So something that humans do on a daily basis, cutting bread, is actually still a big challenge to have robots doing, trying to understand from, again, visual perception, force torque perception, what kind of bread the robot is facing, how the knife should be inclined, what kind of force should be used, and to what extent one can do this with one arm, or whether the help of the other arm to use it as a tool, of course, is also necessary. And then, of course, the physical aspect, or physical human-robot collaboration in direct compliance tasks, trying to understand or build systems that are natural to human. And by natural, generating motions that humans do not get scared of when they interact with the robot having the ability to communicate in right terms what it is supposed, or what is to do next, and how can this be properly encoded so that the challenge, that the feedback to the human is done both through the visual, but then also force torque and haptic channels, as well as using dialogue. So the things I would like to talk about today, and that I will go through, are the works that we have done in this area. I will talk very much about object grasping and manipulation, since I think that this is still a largely open and unsolved problem in the area of robotics. In-hand manipulation, so once the object is safely grasped by a robot, how can in-hand manipulation and dexterity available to the robot be used to prepare the tool or the object to be used for a specific task? Why understanding human grasping is important, both from the perceptual point of view in terms of having information of how robots can learn to grasp, but also how the information can be used to build robots that are as good as humans when it comes to dexterity, for example. I'm going to talk a little bit about integration of motion and grasp planning, because robots moving in the environments actually need to be able to not only plan how to grasp things, but also where to place them, how to put them down, and again, take into account their own embodiment. And I'm going to finish up with some examples of how this affects or can result in natural human-robot interaction and collaboration. So one of the tasks humans do very good on a daily basis is interaction with physical objects, and interaction with physical objects in pretty different media. So washing dishes is maybe not something that we anymore do as often now with all the dishwashers and so on. But this is just one example of how dual arm manipulation and using different types of deformable tools, and also without really understanding or being able to convey the physics of the task that the human is doing here, is something that comes very natural to us. And these are some of the things we would like robots to do, but today there are no robots in the world that can do anything remotely, even close to washing dishes. So Jan LeCun, I think, this morning said that we still have robots that can't fill in and empty a dishwasher, so this is yet another, I would say, level of difficulty. Now, what is interesting here is that humans are very good in understanding that if I hold a porcelain bowl, which is covered by water, dishwasher powder, or oil, requires different types of force to be applied. However, I don't know how many newtons that is. I don't know what kind of torque I use in order to be able to do this. So all these things are in a way hidden or latent to the robot when the robot is observing a human doing this. So if you think about classical work in object grasping and manipulation, and we can say that we are now in, let's say, 45 years of research in this area, both building robot hands, but also putting up the basic equations for understanding stability of objects and so on. there are still, again, pretty big challenges, and one of them is, of course, due to the limitations in hardware and also the limitations in perception. So the video on your left hand or right hand side is our recent work on basically finger gating or finger adaptation when the objects held by the robot are getting perturbed once the grasp has been applied. There are 3 finger grasps, as you see here, and we are basically using some optimal control here. I'm not going to go into the details are in the paper. But the idea is basically to assess online the stability. So these videos are not sped up or anything like that. So this is what we could do. So what you see here are robots performing finger gating in a similar way as we humans do. So if you have something, you hold something in your hand, the things start sliding because it's heavier than you expected or something like that. You first try to apply higher stiffness. If that doesn't work, and it won't, in case if you, for example, like in this case, hold a plastic cup, the nominal force or the absolute force that you can apply is limited because it will destroy the object if you just continue to squeeze more and more and more. So the idea is here then to try to do finger gating, so get better hold of the object, so holding the object with 2 fingers, moving the 3rd one in order to get a more stable grasp and so on. So, and then of course there are other types of limitations like dynamics that can potentially come from interacting with the environment or having a human, like in this case, perturbing the pose of the object in the hand. And I would say that this is where today, this is what the state of the art is, looking into then the force torque feedback, or in this case, the readings from the syntax sensors, and trying to understand really the set of forces and torques that a certain grasp can withstand, and do this in real time. Now, why is this important? Well, for quite some time, we have been working on the problem of understanding human grasping for a couple of different purposes. One purpose is, of course, if we can understand how humans use their hands in different situations. We can also build and use this information to build better prosthetics or better robot hands. Lots of the work that we have done has also been used in the teleoperation and gaming industry, so generating very realistic visualizations of human body motion, and specifically human body motion in interaction with objects. And of course, a big area of research, learning by demonstration in robotics, if a human is to teach a robot how to perform or how to interact with the environment, or in particular objects, by understanding human grasping, we can provide an input to the learning system that then allows robot to learn better or faster how to perform different task-related grasping on an object. And why is task-related grasping relevant? Well, it is relevant because object grasping is not only about grasping an object, picking up something, but in most cases, we humans pick up something in order to do something with an object. So it's very much task-related, dependent on whether we are picking up a tool or scissors. We are doing that for a purpose. So in robotics community, the problem of grasping has been, as I have said, addressed for 40 years now, but task-related grasping really, out of almost infinitely many grasps that can be applied on any object, choose or be able to choose those grasps that are actually relevant for the task. And that is very much embodiment dependent, right? Because it depends on how many fingers one has, and also depends on the task itself. So picking up an apple to hand it over to somebody or just put it in the box will very much depend or affect how that apple should be grasped. Jan LeCun talked also today about common sense reasoning, planning, and so on. And this is also an area that we have been working on for quite some time. And there are rather simple things that we humans, again, take for granted. So robot bring me something to drink or robot bring me something to drink from are two completely different tasks. And thinking of resolving then the spoken command and generating the right set of, let's say, both perceptual and control modules in order for the robot to be able to do that requires actually quite many steps to be fulfilled. So this is just one example of the work that we have done 5-6 years ago. We encoded lots of knowledge about objects and different types of hands with Bayesian nets, looked into how we can also encode and learn the stability requirements, for example, understand how glass should be picked up in order to pour a fluid in it or just put it upside down in a dishwasher and so on. And also we have demonstrated how to actually execute these tasks in realistic settings. So have a table filled with different types of objects and use then the available object recognition, categorization, and so on systems in order to be able to show that this was doable. But apart from that, we wanted actually to have a system that can do three things at the same time, use the same type of system to observe humans in natural settings and perform action recognition, so understanding what the fingers are doing, what the hands are doing in interaction with objects. Use this for task-based planning, and at the same time, based on then physical condition, understand what the stable grasp means or what the stable grasp for a specific task actually means. This is just one example from a 5-year-old work. Again, what you see here is full pose or hand tracking, 26 degrees of freedom hand tracking in interaction with objects. So what we are doing here, we are basically using hand tracking together with an Bayesian net system to assess and generate the training data that we use later on for understanding better which degrees of freedom are involved in different tasks and so on, to understand or predict, and this is also something that Jan has said this morning was important, trying to predict what a human is going to do next. And this is extremely important in human-robot interaction tasks, trying to understand the human's intention so that the robot can act accordingly. So what we could do here from hand motion or full pose tracking, understand which object the human intends to interact with, and how the fact that the hand is used in a specific way, what would be the task, most likely task that the human plans to do. Why was this important? Well, we generated lots of data and started to look into different types of clustering techniques, nonlinear dimensionality reduction techniques, such as GPLVMs, Gaussian process latent variable models, in order to build manifolds of human hand actions and try to understand how this information can be then used for things that I have said before, design new types of robot hands or design those types of robot hands that can cover a specific part of the maybe human action manifold and can satisfy certain requirements that a robot would need to do. So if you have a robot that would need to fill in or empty a dishwasher, or if you have a robot that would need to, let's say, clean windows or pick up things and so on, maybe different types of hands would be needed. So we worked with prosthetics developers, we worked with robotic hand developers and looked into different types of hand designs and used this information of human hand action manifold to compare different types of hand designs, both the anthropomorphic ones and non-anthropomorphic ones, to look into what kind or what part what portion of the human action manifold a specific hand design would result in or cover. So we could do, let's say, optimization of the different types of hand kinematics and say that this type of hand with this number of degrees of freedom would be able to do this type of tasks. And I think that this is the understanding we need also for the future, because I'm not saying that we necessarily need to kind of copy human dexterity, but we need to find a way of how to understand human dexterity and also build robot hands that can cover a specific part of the human dexterity space. Now, grasping is very much about then the hand design, but also understanding what type of grasps or what type of objects one can interact with. And for that reason, I don't think that we can study this as two separate problems as these commonly were. So you build a hand and then you use that hand for do stability assessment and generating grasps and so on. So we started to look into techniques that we named grasp moduli spaces, where we wanted to then achieve a common representation of, or build a common space of grasps and shapes. And this was our early work. This was back in 2013, and I like to call it actually the transfer learning through then mathematical formulation of both cylindric coordinates that represent the basis of generating different types of objects, but also at the same time transfer the stability of the grasp. So what you see here is just one example. We go through a continuous transformation between a book and a bottle. And what you see are the three vectors representing a three-fingered grasp, stable grasp on the object. So we can at the same time continuously transform the shape of the object and also in real time generate three-fingered stable grasps on the object. So what happens here, and there are many trajectories of course that one can take here, is that by knowing, for example, how three objects defined by cylindrical coordinates can be grasped, we can build a space, continuous space of, well, basically in this case, infinitely many shapes of objects where we can transfer the knowledge in a continuous manner of stable grasps between different types of shapes. And there are, for those interested, there are many more examples of these in the papers. And we also talk about addressing then uncertainty in such systems. Now, grasping itself, for me, has always been a temporal problem. So, as a human, I observe a scene, I have a task to solve, I find the object or a tool that fulfills that task. I generate a specific grasp, I pick up something, most likely I will change the pose of that object or tool in my hand, and while using it, so while performing a specific task with that object, applying some form of external force like you see in a video a few slides back, I need to be able to, the grasp needs to remain stable. So what I think is important is that for those working with interaction, physical interaction with the environment is to really understand the process, and that throughout all this process, we actually need to have a real-time feedback system that in most cases will be based both on visual feedback, but also on the force torque feedback in order to be able to then have the stable grasp remaining. Now, why is this important? From the beginning, I have also looked very much into not only a single hand grasping, but dual arm grasping, and trying to understand how most of the off-the-shelf robots that we can buy today that still have rather simple fingers can use then the available degrees of freedom in order to, let's say, interact with the environment and the objects in a best or the rich, as rich way as possible. So the recent work will be presented after summer at IROS this year, addresses a little bit of this dual arm in-hand manipulation problem through so-called dexterous manipulation graphs, where we actually look into the problem of if a robot that has only 2 fingers, and I just need to say most of the robots today are still rather simple and are equipped with only a dual finger system or like a small picker. So if they succeed to pick up an object, in most cases this object will not be in a pose from which it can actually be used for any kind of task. So if you go now back and remember those, that slide with the spatula, the robot either needs to use a pre-manipulation, and even with pre-manipulation sometimes it will pick it up in a way so that it cannot use it to flip a pancake or something similar. So what we are developing are now systems that are based on dual arm interaction. So having systems that can actively change the pose of an object in the hand in order to then use it as a tool. Now, once the object is grasped, as I said, it needs to be also used. In many cases, it also needs to be placed down. And one of the problems that robots are, of course, facing today is to work in cluttered environments. One big problem here is the narrow free space passages, of course. Robots are still big and bulky, and hands are big. Objects are that robots are supposed to interact with have been adapted to our bodies, so have both the shape and size that is more, let's say, adapted to our hands. So lots of the work that we are doing is then looking into the problems of how grasp and motion planning can be used together with, of course, different types of perception to understand both how objects should be grasped in cluttered environments and also how we can use the same type of methodology to place objects in environments that are rather cluttered. So this looks then into some of the classical motion planning problems and methodologies together with, or equipping this with reinforcement or integrating this with reinforcement learning and generative adversarial networks in order to generate heuristics for, let's say, finding fast the trajectories in high-dimensional motion spaces. And let me just show you one video. Apart from being able to then demonstrate that we can actually, with different types of embodiments, different types of robot hands, execute this in rather cluttered environments. What we are also learning is how one can then use displacement of object, or what we call non-prehensile rearrangement planning, in order to move objects or change actively the environment so that we can make it possible for certain objects to be placed. So what we are looking at are some of the classical problems, of course, in the case of obstacles, and the non-prehensile rearrangement planning is about pushing things around, not necessarily applying grasps. Which becomes really interesting if the problem, if you start to scale the problem and you're moving more than one object and so on, and how to do this by then understanding also the outcomes of your actions. And this is something also that Jan LeCun mentioned this morning, that most of the systems today are not able to look into the future significantly and look how the certain action, when you push into something, actually result in a specific motion of the object. So this is what we do. We are looking into how reinforcement learning basically can be used to then find appropriate trajectories for moving around several objects, and then integrate this with more classical methods for motion planning in order to do the complex problem of rearrangement planning in cluttered environments. So this is rather novel work, and for those interested, I can provide an archive paper, and then there are also lots of examples and the code that one can test. Now, all this is important to us because robots are supposed to work in rather complex environments, and when it comes to then human-robot interaction, it is extremely important to have robots that can interact with humans in a natural manner. So we are looking into systems that can both predict human behavior, that can communicate their own behavior, and learn to collaborate with humans through direct and physical interaction. And this is also something that calls for this solving the problem of prediction, because in order to be able to generate natural motion for a robot, one needs to predict what the human is most likely going to do next. So prediction, I agree with, again, Jan LeCun, is extremely important thing. So a couple of years back, we then started to look into human motion tracking and the work that has been done in human motion tracking and using recurrent neural nets and so on. So the idea was to develop a system that can give 1 to 1.5 seconds of predictions of human motion. For the purpose of then adapting different types of collaborative control algorithms, model predictive control, and so on, so that a robot can generate a more natural behavior. So there has been some work in this area in, of course, understanding human motion and doing this with both deep nets, different types of recurrent neural nets, and so on. But when it comes to human-robot interaction, this is not an offline system. Of course, we wanted something that can predict this in real time based on rather short history. And again, as it has been mentioned this morning, we don't want to predict a single or average over many different types of possible future motions, because as Jan has said, if you just average an image, you're not going to get the good information. So what we want to have is a system that can have a distribution over possible future motions and determine then how likely each of these are based on the past. So let me just go through a little bit. So we then build different types of network structures. We assess different types of representations based on human skeleton, and looked into how different types of temporal encoders using symmetric structure, convolutional temporal encoders, hierarchical temporal encoders, and so on, what that results in, how much training data we need, and so on. So this is from CVPR last year. And we got really interesting insights from this initial work, but what we could see then from the also different network structure, and that different neurons basically could encode different types of what I would call primitive motions, so whole body turning, crouching, arm movements, and so on, which I think is also very related to what we have seen that these types of networks can do in terms of language, in terms of image understanding, and so on, given again the compositional structure of the world that was mentioned this morning. So these are just some examples of then how we can use individual neurons to as generators of different types of motions, something that just basically falls out of the network in a very a nice way. But what is also interesting is that this the representation that we also trained can give us what we call long-term prediction, 1.6 seconds. I don't know whether that's again enough, something to be seen, but at least when it comes to compliant motion, when it comes to robots and a human carrying something together and so on, 1.6 seconds is quite enough. So of course, what we started to then look into in more detail, something that we recently presented also at IJCAI, how can we also measure the uncertainty, try to understand how uncertain models are, and use, of course, assess this in real situations. So the next step was to then look into conditional variational autoencoders and look into different types of structures that can then give us this prediction over time. So this is how it looks, a human basically standing in front of the robot and performing some very easy everyday motion, waving in this case, and the yellow lines that you see here are this 1.6 seconds prediction of most likely human motion, just to give you a little bit of an idea of how it looks. And I think that this is very interesting because also there are applications which are not only about the physical interaction, but are potentially also relevant for learning by demonstration. So, of course, why is this important? Well, it's important because apart from just generating or assessing what the human is going to do next, and robot adapting, it's also very much about learning. So part of the task, part of the, or one of the problems that we are assessing is how then the human and the robot can, through having maybe a common goal, how the robot can learn then its own behavior through reinforcement learning in this case by just being given a terminal feedback or terminal reward in a way. So the idea here is that the robot is interacting with the human by, again, direct physical contact, and the idea is to learn how to adapt or how to generate motions of its own hand, where the task is then to have the ball in the middle of the thing that the robot and the human are holding together. So we have newer work in this area, so for those interested, I can provide references. But the idea is then to assess also different types of dimensionality and looking into how a robot can then adapt to the human and have the right level of the adaptation based on whether they have a common goal or whether they are actually playing a game where one needs to win over the other and so on. Now to sum up a little bit with the things I also find relevant for the future, and it has been mentioned this morning that when it comes to using CNNs and different types of deep learning structures, reinforcement learning in particular on robots, one of the big challenges is to actually generate enough data. And I agree. I think that having robots just blindly for a long time interact with all types of different types of objects or with a human is just not a feasible way of doing that. So what we looked into and what we are looking into right now is to what extent we can use then a way of representing the right type of, let's say, degrees of freedom and learning the representation with using encoder-decoder networks of different sorts and have robots through reinforcement learning then learn tasks fast and efficiently by also assessing then the use of the simulators. So this is just one simple task that we have here, robot learning how to throw a ball on a Pokemon figure here, and learning this from very few trials. So if you now think that the robot has 7 degrees of freedom in each arm, and if you think that the size of the image can be rather limited, but maybe, I don't know, 100 by 100, 400 by 400, the Pokemon can be anywhere in that image, and also then generating the right trajectory in time, so maybe 20 to 40 time sequences that you need to learn, very soon the problem from the reinforcement learning point of view becomes quite complex. So what we looked into is whether we can, in a smart way, build structures so that we simplify the perception superlayer and behavior superlayers, so that in the middle we have so-called policy superlayer, where the policy does not go from 400 to 400 maybe image and then 20 multiplied by 7 degrees of freedom. If you think 20 time steps multiple 7 degrees of freedom, but build a policy superlayer where then the encoder-decoder structure can be used more as the dimensionality reduction problem. And this is what we looked at for different types of tasks, both grasping and throwing the ball here. So in principle, we looked into how then the predictive policy training with reinforcement learning can be then implemented in a smart way by using different types of dimensionality reduction. So for those interested, there are more details in the recent work here. And the idea, of course, is then to do lots of training in simulation, how we did the transfer of the knowledge from the simulator to the real world. Come and talk to me afterwards. I think that my 40 minutes are gone, so I'm basically going to end up with some of the challenges that I see for the, I would say, area of robotics, area of computer vision, machine learning, and of course AI, when it comes to then having physical systems around us and doing things that we humans are doing on an everyday basis. I think that interaction with the environment is very much embodiment related. And to us humans, certain things are very, very natural to do. I've seen a couple of papers today where humans are used to kind of help robots to find solutions when the motion planning problem becomes too difficult and so on. I think that the understanding of the embodiment itself is a very interesting problem. So we need to somehow be able to assess what a robot with 2 fingers, 3 fingers, armed with 7 degrees of freedom and so on, is actually capable of doing, rather than just blindly generating the data and having robots in a way be programmed, or that the motions are generated by the human in a similar way as humans would do. Encoding relations between tasks, and I think that that's also in itself a really interesting problem, whether we want to talk about transfer learning or something else, I really don't mind. But what I think here is that we still see lots of papers addressing individual problems, let's say segmentation, detection, tracking, recognition, and so on. Very few systems today that are actually able to go from perception to, for example, grasping and in-hand manipulation by not solving all these problems individually. So I think that there are still things to do here, understanding how the data is represented and how learning of both, let's say, low-level motion planning and high-level decision-making, semantics and so on can be solved in an appropriate way. And that, of course, is closely related to what data we generate, in what kind of situations, what are the tasks we want robots to solve. And this is, of course, going to be very dependent whether the robots are to solve tasks autonomously without interacting with humans, or whether there is a human in a way in the loop, because I think that then we actually need to understand also very much the behavior of the human, and how that behavior, or how the robot should adapt its own behavior in order to make the interaction as natural as possible for the human. And of course, one of the things that we have been working with for quite some time, multisensory systems. I think that today we still see quite a few systems that solve visual perception tasks, but understanding how the visual and haptic channels maybe should be integrated in then close interaction with the environment, I find very interesting and rather unsolved problems. So I hope that there will be more people, especially here in the audience, addressing some of the problems in this area. So thank you.
Yeah, great talk. I wonder if you can comment on the general value function framework in terms of, storing predictive knowledge in the value function, how that might be relevant to prediction and robotics in general.
So you mean how we do that, or how we...
No, how the general value function framework, because like a couple of days ago in the workshop, Richard Sutton and is promoting this framework in terms of continual learning and really represent the predictive knowledge in this framework.
Yeah. I think it's a big challenge because I think that the complexity of the task that we would like to solve and then also the computational frameworks that we are using today and the methodologies that we are using today are just kind of like not compatible, I would say. So the work that we have done, that I presented very shortly here, is trying to really understand the dimensionality of the problem. And I think that sometimes we are just solving blindly the tasks without really understanding the dimensionality. So I think that if we first start to understand what are the relevant, let's say, parts of the configuration spaces that are covered for a particular task and so on, we can use this information to then build hierarchies in a better way than we are doing right now. So I don't believe that there will be like a single reinforcement learning system that can solve everything. I think that also Jan LeCun mentioned this morning, that we need to some way of encoding partially the logic and partially the common sense knowledge and try to see how these systems, in a way, how different types of methods can be integrated. So this is one way of doing it, finding a way of simplifying the dimensionality and then using simulation to generate lots of data. And then the other step would be integrating different types of methodologies for addressing that.
Okay, thanks.
Okay, so thank you very much. So I want to ask about the kind of representations for prediction. And in this kind of deep neural network, original input comes from the 2D image. And in the conventional robotics, we would map that into a 3D spatial representation or a joint angle configuration space or a skin surface space separately. But in application of a deep network, do you think we need to create such explicit representation from different framework representation, or like a mixed hidden neuron population implicitly capture those different features?
So the work that has been presented at IJCAI is actually using 3D information, so it's tracking the human skeleton in 3D. So yes, I think that 3D is extremely important, especially when it comes to interaction with objects. So the videos seem 2D, but the information that we used is actually 3D.
Thank you very much.